Okay, so welcome to today's review session. What we covered last week was okay. I'm going to stop messing around with this thing. Okay, what we covered last week was a lot of intro geology. So we learned a little bit about how the Earth is structured. I didn't go into a lot of detail because I alluded to the fact that if you want to define the layers of Earth by chemistry versus physical properties, you're going to end up with different sets of layers. I alluded to that when I mentioned that the lithosphere, which is what tectonic plates are made of, actually includes the crust as well as the uppermost part of the mantle. And those are layers of Earth that are defined by chemistry. And I can't completely avoid alluding to those because, well, the crust is where most of the action happens with geology. And the mantle is fundamentally what moves around to cause plate tectonics. But somewhat confusingly, the physically the top of the mantle moves along with the crust, and that's what makes up the plates. But I will get to that. We moved into Continental Drift and how that was sort of a precursor theory to plate tectonics and how it put together a lot of the important evidence like fossils and coastline shapes, but there wasn't a mechanism developed for it, and that couldn't come about until seafloor spreading and subduction were discovered under the ocean, and people were able to see, okay, new crust is being formed, the crust is going somewhere. It turns out that the continents have moved because Earth's surface is made of these pieces that move around relative to one another, and that's plate tectonics. And we spent a lot of the rest of the lecture talking about different types of plate boundaries. And the lab that is up for this week and due this coming Friday is on plate tectonics too. So I won't be going over the lab that much, but I'll be talking a little bit about some potential connections with lecture here. So on that note, the plate tectonics lab is due Friday, and it's based very heavily on lecture 5. So if you're watching this and you have not yet gone through lecture 5, do that, obviously. But something else I want to mention is that the first reading assignment is open. I haven't seen anybody submit to that yet. It's not due until the week after the midterm. But if you want to get a head start on that, you can find it either under the assignments tab on Gaucho Space, or you can go to week 6, Glaciers and Ice, which is when it's due, and that's where it shows up. So you can access it and open it now, even if it's still a couple weeks off from the deadline, but it's getting closer and closer and closer, as is the midterm. The midterm is actually going to open up next week, Monday, February 1st, and it will be due Sunday, February 7th. And I will be posting a study guide later this week, and there will be more midterm review coming up. But that's going to open up next week, just so that you're aware of that. So going to the structure of the Earth and continental drift, some of the big takeaways from last week's section are that Earth is composed of physical layers, so layers that behave differently depending on whether they're solid or liquid, and if they're a solid, whether they're a rigid solid or a more plasticky solid that can kind of flow. So Earth, the outermost 2 layers and the ones that we really care about are the lithosphere, which is the crust and the uppermost part of the mantle, and that moves, and that is a rigid solid. That is brittle and hard, and that actually makes up the plates. And those plates of lithosphere flow on top of the asthenosphere, which is a part of the mantle that is solid, but it can flow kind of like the way silly putty does, and actually similarly to how glaciers flow, as it turns out. Glaciers are a really good example of a solid that flows. And this is the basis of the plate tectonic theory is that the surface of the Earth is made of plates of these lithosphere, and they move in different directions relative to one another and have done so since Earth was formed. And that is true. Something interesting to note about Mars is that Mars formerly had plate tectonic, or Mars is geologically dead, essentially. Mars actually never developed plate tectonics. And that actually, some people think, has quite a bit to do with why Mars does not support life, because volcanoes actually play a big role in regulating climate by releasing carbon dioxide. But I'm getting a little bit off track there. In any case, we know plate tectonics exists now, but we didn't until pretty recently. Scientists came across evidence that it turned out would also be really compelling evidence for plate tectonics, but they came across this evidence before they had the means to figure out a mechanism for why the continents appeared to have shifted over time, why there was evidence that the continents have not always been where they are now. And that is the theory of continental drift, which was the precursor theory to plate tectonics. And it's actually quite relevant for Antarctica because one of the main bits of evidence was fossils found on widely separate continents, including examples such as tree ferns found in Antarctica as well as Australia, the same species of tree fern from the same rocks, apparently from the same point in geologic time. And for one thing, that implied that the continents had moved, not just the ferns, but the amphibians and the mammals and all these other fossils that were found, the same identical fossils were found on continents miles apart. So that indicated that the continents had moved because these animals didn't just get there by being plopped there. And it also indicated that Antarctica had once had a much less, sorry, the light's all messed up. Antarctica had a much more mild climate once upon a time because they were finding fossils like tree ferns there. There had been forests there. There had been lots of land animals there. And something we'll talk more about in lecture is that there aren't a lot of land animals left in Antarctica at all. The largest strictly land animal left in Antarctica is the midge, which is an insect. So that many land animals being there at all indicated that the continents had probably moved around. Either Earth's climate had changed, which it has, or the continents have moved around a lot. The other bits of evidence included the fact that the continents, the coastlines of the continents when mapped, in some cases seem to fit together. Africa and South America are the most obvious example, but Madagascar is another good example. It's been separated by rifting from the rest of Africa. And I need to double check this, but I'm pretty sure the division between Papua New Guinea and Australia is an example of that also. I'm pretty sure there's a small rift there that separated those two. And that's just, again, something that came as a result of map making. The third line of evidence was glaciers. And we know a decent amount about glaciers. We have glaciers in Antarctica. They found Antarctic-style glaciers, glaciers at sea level, or they found evidence of Antarctic-style glaciers that got to sea level and pushed sediment out to sea in places like South America and India, making it pretty obvious that those continents had been also either under really cold temperatures at some point, which they had been, or had moved also, which they have been, which they did. And that's one thing to consider about some of this evidence. It's not 100% this, it's not 100% this only says that continents have moved. You have to also consider how has Earth's climate changed, and that's something that scientists do have to consider when looking at fossils. They're not just interested in where the continents have been, they're interested in overall global climate, which is something we'll talk more about in this week's lectures. But then the last bit of evidence was the fact that the same rocks were found on different sides of the same ocean, that mountains that lined up were found on either side of the Atlantic Ocean, that rocks that resembled each other were found in South Africa and Australia and Antarctica. I mentioned the Trans-Antarctic Mountains as one particular example of a geologic feature in Antarctica. I mentioned how the Trans-Antarctic Mountains are one side of a rift shoulder where the crust has been shoved up on either side as seafloor spreading is occurring, and they found evidence of the other rift shoulder in South Africa. And those are examples of geologic structures being found and indicating continental drift. And this would eventually lead to the discovery of the plate tectonic theory. The discovery of plate tectonics only happened once people could really see what was going on under the ocean, because firstly, they discovered the mid-ocean ridges where seafloor spreading is occurring. Seafloor spreading is the creation of new oceanic crust at mid-ocean ridges. It then spreads out to either side, and it will eventually get recycled in subduction zones or trenches like the Marianas Trench. And those were also not really well known until ocean exploration had improved quite a bit. So some other takeaways. So they came up with the evidence that seafloor spreading was occurring. They strengthened that by looking at what the rocks on either side of the spreading centers were like. So they hypothesized, okay, if crust is coming out of these volcanoes and being spewed out to either side, that means that we should see some evidence. That means the rocks should be the same age on either side of the spreading center. They should be the same density, more or less, because they've cooled to the same extent since being erupted. And they should have the same magnetic signature. They should show the same switching of magnetic polarity. And all of these things were found to be the case. And we went into a little bit of detail about what drives plate tectonics, what's known to drive plate tectonics today. We talked about the combination of ridge push and slab pull, how the fact that that closer to the spreading center, the rock is warmer and less dense, and farther from the spreading center, it's colder and more dense, and that causes it to sink down more. And that actually causes a slope between the rock that's right at the spreading center and the rock that's further out. And that slope helps the plates move outward. It's similarly, that's ridge push. Slab pull refers to the fact that the downgoing plate actually helps drag the rest of the plate with it. Largely because the minerals in the plate become metamorphosed and become a lot heavier when subduction is happening. And as they become heavier and denser, that drags the rest of the plate along with it. And it's all driven to a big extent by convection of material within the mantle. As far as plate boundary types, divergent, convergent, and transform are the three you need to remember. There are some other terms, and I'll talk about how they're relevant, but divergent boundaries are seafloor spreading, mid-ocean ridges. And that's where you have plates moving away from each other because you have magma spewing up at the central mid-ocean ridge, and then the two plates are moving away from each other on either side. The rock, the one way to think about it is that the magma comes up at the middle, and that kind of makes the plates on either side. You have two plates being formed and spreading away from one another. And in Antarctica, the entire continent is actually surrounded by spreading centers right now. Antarctica itself, the coastline is not located at a plate boundary. The plate boundaries themselves are further out in the ocean where the spreading centers are. Antarctica is what would be called a passive margin, meaning that its coastline is not where a plate boundary is right now. At a convergent, okay, that was just what sorry, my cat did something. There we go. At a convergent plate boundary, you have plates colliding, and a couple of things can happen. Usually one of them subducts. Usually the denser plate will subduct, whether that's an oceanic crust plate subducting under a continental crust plate, or if you have two oceanic crust plates, the more dense one will subduct. If you have two plates made of continental crust colliding, you will get a Himalaya type situation. You will get mountain building. And something I put in here that I forgot to mention until just now, I talked a little bit about how you get different types of volcanism at different plate boundaries. So at divergent plate boundaries, you get volcanism by the pressure dropping. The pressure drops from the plates being pulled outward, and the solid mantle coming up actually can melt because of the pressure drop. At convergent plate boundaries, you have subducting plates bringing down sediments, and that has water in it, and that helps lower the melting temperature enough for the mantle to melt. And then at transform plate boundaries, you don't have volcanoes at all. The transform boundaries are the segments that move, they move without going up or down at all. They just move at the same level in opposite directions. And they usually exist as the connector segments you see between the different ridges along a mid-ocean ridge. And I have a slide on, I have a diagram of that on the next slide. But you don't usually have, you don't have volcanism at transform boundaries. I also talked about something called a fracture zone, how when you go far away enough from the spreading center, the plates sort of appear to be going in the same direction. That's because you don't really have a plate boundary there anymore. You're far away enough from the spreading center that that the crust is moving in the same direction on either side of the fracture. And the fracture zone exists because at one point it was where the crust was shorn apart like this, was shorn apart horizontally along the same plane in opposite directions like a transform fault. But the fracture zones are kind of like dead faults that where there was movement possible before, but there isn't now. And don't overthink fracture zones too much. You can kind of just think of them as dead faults. And as I'll talk about when I talk about the lab material a bit, you can pretty easily identify a fracture zone by the fact that you have two arrows just pointing in the same direction, like two lanes of traffic. If you see that on either side of what looks like a plate boundary, it's not a plate boundary, it's a fracture zone. I also talked about hotspots, and hotspots are not a plate boundary type either. They're a rare case where an extremely hot plume of magma rises. You can see one in this diagram here, actually. There's a hotspot out in the ocean. And this plume of magma is strong enough to just go through the plate, and it's hot enough just to melt and produce magma as it is. That's kind of why they're called hotspots. It's hot mantle material rising, hot enough to melt. And you actually do have this in Antarctica right now. The volcanoes in Antarctica are not caused by spreading centers for the most part, because that's out in the ocean, or by subduction, because you don't really have any plate boundaries along Antarctica itself now. You do have some subduction along some of the microplates near South America. The subantarctic islands are made by subduction, but Antarctica itself doesn't really have much of that, but it does have a few hotspots, like the one causing Mount Erebus presently. I did also want to mention that it's good to get an understanding of what differentiates oceanic and continental crust. Oceanic crust is dense, dark-colored, or mafic, as you're going to learn in lab. It's thin and it subducts because it's so dense. Continental crust is buoyant, not so dense, felsic or light-colored, and it's thick, but it's thick in this. It's kind of thick like whipped cream. It's thick, but not. It's thick and light, relatively speaking. You would never say a rock was light, but compared to oceanic rock, it's very light, and so it doesn't subduct. It's too buoyant to subduct. So that's why if you get two plates made of continental material colliding, you get mountain building instead of subduction. So that's a summary of what we went over last week. In terms of how this connects to this week's lab, I will say make sure that you review Lecture 5 if you have not attempted the lab already, and the TA's presentation has some really helpful diagrams. Now, regarding plate boundary movement, it's all going to be about the arrows. With this zone here, you can see how the arrows, this is actually this gives you a nice side view of a spreading center. And the thing you have to remember about spreading centers is there's two types of plate boundaries there. For the most part, we think of them as divergent zones because there are these mid-ocean ridge segments where you have crust coming out from either side. You can actually see how there's a little bit of a slope here. It's very subtle, but you can see how it's raised higher, closer to where the magma is coming up than it is farther away, and that's because farther away the rock gets colder and denser, and so there actually is a little bit of a slope. The beige stuff you're seeing on here is meant to be ocean sediments. But you have this mid-ocean ridge segment, and they are usually staggered. You don't, physics-wise, it's very hard for you to have just a single long fissure. So usually you have a bunch of staggered little fissures, and because of the way they're aligned, kind of between the fissures, you have this zone where you have crust moving horizontally in opposite directions, and that's the transform fault. The thing, and one thing I should mention also is that a lot of the animations in Lecture 5 come from Dr. Tanya Atwater's website, and there's a link to that under course resources at the top of the Gaucho Space page in case you want to look through any of those animations. But the animations will sometimes give you a sense that spreading centers, the rate at which they spread will change, and that's something that lab talks about a little bit, and that will cause the length, like how you see there's just this little oh, I see there's a question in chat. You can identify the fracture zones by the arrows, and I'll get to that in just a second. But you can see that there's a little, you can see that the active transform fault is this long right now. There's a set distance between one of these spreading centers and the other. If the rate of spreading changes rapidly, that can cause the length of the transform section to change. And that's kind of what causes the fracture zones. Because let's say if this, in this particular example, if the transform fault got smaller, like if the two spreading segments got closer together, what that would mean is that along this stretch of the line, part of what was formerly going in two different directions, since this section that actually is experiencing active transform faulting is much smaller, you have a larger section where the plates are just moving in the same direction. Or to put it another way, actually, the green line represents a plate boundary, and that plate boundary actually ends up including both divergent segments and convergent segments. Or excuse me, not convergent and transform segments. And the transform segments occur when the plate boundary kind of has to make this leap over from one mid-ocean ridge segment to the next. And hypothetically, this could actually get wider again. The transform, you could have the two spreading centers move farther away, and the transform fault segment would get longer. And what that would mean was that this area that is the fracture zone on the diagram would again become a transform boundary. But if they were to get closer together, you would have less of that line being the transform boundary and more of the fracture zone. It's a bit of a hard concept to get. This is why I try to emphasize that plate boundaries are not static. And one example of it is that if the rate at one of the spreading centers changes, that can cause the spreading centers to get farther apart and make the transform fault longer or shorter. And it's going to get longer or shorter like along this line that in this diagram includes both the active transform fault and the inactive fracture zones. The fracture zones can again become transform boundaries, but they're not transform boundaries now. The transform fault can get wider or narrower, and the fracture zone is kind of just the part that's not being used right now in a sense. Don't overthink fracture zones. This isn't the best example, but if you look at the arrows on the bottom side of the transform fault, there's an arrow that's pointing towards the lower left side of the slide. And then on the upper side so it's kind of hard to see here, it's by the transform fault itself. And then there's another arrow you'll notice on the other side of the crack over here showing also movement towards the lower left side of the screen. And the crust here, where my cursor is right now, is moving in the same direction as the crust here, where my cursor is now. If you're over here by the transform fault, the crust is moving in different directions. If you're here where the transform fault is marked, the crust is moving in that direction here, and then in that direction here. So I'm going to open the floor up to questions because that was a lot. And I talked a lot more about fracture zones here than I did during lecture. I'm not going to emphasize them a huge amount on the quizzes or the exams, but they come up in lab, which is why I wanted to linger on them a little bit. So recording is on right now. Does anyone have questions that they want to put out while we still have the recording on?
Could you elaborate on like what isostasy is? I think that's how.
Yes, isostasy. So isostasy is it's something I actually talked more about with geography, but isostasy is this concept that things that are heavier or thicker are going to weigh more down into the asthenosphere. And this mostly relates to thick crust versus thin crust. The gist of it is that if you have crust that is very thick, it's going to sink more into the lithosphere. And in Antarctica, an extra added element is that you have not only thick crust, but you also have the weight from glaciers. And the weight from glaciers also literally causes the plate that Antarctica is sitting on to sink further into the underlying asthenosphere. So it's just this idea, and also a key part of isostasy is that if somewhere in the world something is causing the asthenosphere to sink down, it's going to be pushed up to make up for that elsewhere. Like somewhere else, the asthenosphere is going to rise up to accommodate that. That's not something I lingered on as much, but it's evidence. But it's evidence that the lithosphere is indeed floating on the asthenosphere, because kind of like how if you different blocks or different sized or mass blocks are going to float differently in water. Hey, no biting. The thicker, heavier lithosphere is going to sink more into the asthenosphere than thin. And one takeaway from that is that continental lithosphere sinks much more. Something I'm going to talk about in the lecture I'm putting up later is how East Antarctica actually has very thick crust. It's ancient thick crust that has built up for quite a while. But does that give you a better sense of it?
Yes, thank you.
Cool. Anyone else have questions besides Yuriko? Or at least before I shut the recording off. Okay, so that's the presentation for this week. I'm going to shut the recording off and just open the floor. Oh, and I like my cat too. Thank you. She's being a little bit of a pill right now, but she wants to say hi to people. And recording ending in 5, 4, 3.